All right, we're in unit number 6, energy, and page 10, working through example number 5. Example number 5 is all about solar energy, which is a big topic right now and throughout the world. Energy is a big topic, trying to conserve energy. Are there other forms of energy that we can use to live life with? Obviously, fossil fuels are going to eventually run out of them. You can argue about how long it's going to take to get to the end of those, but eventually we're going to run out of those. We need to come up with some other sources of energy. One source of energy would be nuclear power, but eventually, potentially we could run out of uranium. Can't find any more uranium in the ground. But the sun is one that we'll always have. If we don't have the sun, then we're not going to be around. So we'll always have the sun, and so the question is how can we harness that sun to give us energy to live with or to live on? And so this whole exercise is a little bit about how much energy does the sun put out, and ideally how much energy could we take from the sun, and what are some of the limitations that we have in terms of using solar energy. What is its greatest potential, I guess you could ask, and that's kind of what we're going to look at in this particular example. So let me draw out a little bit and start you out on example number 5. All right, so the first part says if the total energy output of the sun is 3.5 times 10 to the 26 watts, determine how much of that energy falls onto the Earth per square meter. And your answer is called the solar constant. So let's get that down first. So we got solar constant here. All right, that answer will be, when we get it here, is called the solar constant, which is basically how much energy per square meter falls on the Earth. Okay, so the next question is this. We need to figure out, what happens to the energy as it leaves the sun. So let's just draw a quick diagram and see what's going on here. So here's the sun. We have to think of this in terms of 3 dimensions. The sun gives off light in all dimensions. So it gives it off, and it's radiating outward. And it's radiating outward in these big spheres. And eventually that energy gets out to the Earth, way out here, about 93 million miles away. Well, if this is the energy that's being given off by the sun, and then not all of that energy hits the Earth. Just a small fragment. The rest of it is thrown out into space. We miss most of it. So you can think of, on a hot sunny day, and you think, man, the sun's hot today. Well, just imagine if you were to collect all of that energy all at once, how hot it would be. It would be blazing hot. So what we need to do is this. We need to come up with a way of figuring how much area is out there at a distance of the Earth. So here's the sun, here's the Earth, and imagine a big sphere that sits out there. And that sphere represents the amount of energy given off by the sun. Now, let's think of it another way. When the sun just leaves when the energy just leaves the sun, its energy is concentrated because the sphere of energy is smaller. As that sun leaves and enters into space, it gets more dilute and more dilute. It becomes fainter and fainter. So the sun's energy per square meter close to the sun is far greater than the amount of energy per square meter way out here. Another way of thinking about it would be with a balloon. So let me just kind of blow out the balloon just a little bit. All right, so let's say that let's say this balloon represents the sun. I'm going to kind of pull this out a little bit, and let's say I take a Sharpie, and let's say I just kind of sketch, just real quick, a square meter on there. And let's say that the plastic that's on the sun, or the rubber that's making the balloon, represents the energy of the sun. And if I were to measure how much plastic would be inside of this square here, that would tell me how much plastic or how much energy per square centimeter. Well, if I were to blow the balloon up, what's going to happen to the amount of energy per square centimeter? Well, let me blow it up a little bit and show you. So I'm going to go ahead and open it up just a little bit and blow it up. All right, and we have something bigger now. Now notice the square got a little bit bigger because we blew it up. But if I were to measure another square centimeter, so earlier I had a square centimeter, now it did change right here, but if I were to look at the amount of plastic or rubber or energy inside this square and compare it to the amount of energy or rubber I had in the previous square, notice that it's stretched out a little bit, so it's a little bit thinner. So as I keep blowing this up, the membrane, while there's the same amount of plastic, the membrane gets thinner. And that's the same thing that happens to the energy of the sun. As the energy of the sun goes away from the sun or enters into space, the farther out it gets, the less energy we have per square centimeter. And that's a good thing, because if we were any closer to the sun, the sun's energy per square meter would be too great and we would fry. And if it was too farther out, it would be too small and we wouldn't have enough energy to sustain life. So there's kind of actually a delicate balance. So what we're going to do is this. We want to figure out, we'll do it right here, the amount of energy that the sun gives off per square centimeter, and that's area. Zoom in a little bit. All right, so, well, we know how much energy. Okay, this is just, you might be thinking, well, energy is joules, this is watts. Well, this is just the amount of energy that's given off per second. So it's another way of thinking about energy. So we're going to say this will be the amount of energy, which we'll use that number. This area is going to be the area of this big sphere. So we need the surface area of a sphere. And we have an equation for the surface area of a sphere, and that's 4 pi r squared. And so we have the energy, and we need r. R would be the distance between between the sun and the earth. And we actually have that number. That's an astronomical unit, and that's on the equation sheet that we have passed out to you. So let's go ahead and plug stuff in. So we have energy, which is going to be 3.85 times 10 to the 26 watts divided by 4 times pi times the radius. So that's going to be the distance between the sun and the earth. And if you look that up, it's going to be 1.5 times 10 to the 11th meters, and then we have to square that. So let's see if we can get all that into the calculator and make some sense of it. So here it is. So we're going to do 3.85 times 10 to the 26. We're going to divide by 4, divide by 3.14, divide by 1.5 times 10 to the 11th, and then divide it again because it's squared. And then I get 1362. So let's write that down. So 13, and that'll be watts per square centimeter. I'm sorry, watts per square meter. All right, now that's an important number. So if you had a square meter and you're above the atmosphere, which is going to be important in just a moment, and you were above the atmosphere, so let's say you had a solar cell that was a square meter, and you put it above the atmosphere, and it was 100% efficient. Well, it would collect 1,362 watts of energy per square centimeter on the average. Okay, now if it was summertime, it'd be a little bit less. If the summertime, it'd be a little bit more. And if it was wintertime, it'd be a little bit less. But on the average, we would collect 1,362. So if you had 100-watt light bulbs, you could run basically 13 100-watt light bulbs at that point in time. And you think about it. If you got a big house and you've got a lot of light bulbs on, and you're supplying the energy for this house with solar energy from this solar cell that's at the top of the atmosphere, and that solar cell is only a square meter, you're only able to collect enough energy to power the lights for 1,300-watt light bulbs. That's the best we could possibly do. So if you want to do anything more than 1,300-watt light bulbs, you're going to have a bigger solar cell at the top of the atmosphere. Now think about that a little bit, because the consequences of that are going to cascade through the next couple questions. So here's the next question. All right, next part. It says, don't forget the energy you calculated must be spread over the entire Earth, front and back. What is your new solar constant? So here's the thought on this. This 1362 is only during the daytime, at its maximum point. At nighttime, you're not going to collect anything. So if you want to operate your house off of this solar panel, 1362 is not what you're going to get all the time. You're going to get something far less than 1362 because that solar panel is going to have to go through nighttime periodically, once every 24 hours. And it won't always be in its, best spot. If it's the solar panel is out during sunset, it's not going to collect as much energy, or sunrise, it's not going to collect as much energy. So we have to have some way of determining, well, how much energy will it get on the average? Well, we have a way of thinking about that. And it goes back to the equation that we used just a little bit ago. 4 pi r squared is actually the area of a sphere. But now look at that equation. What is this? Isn't that pi r squared? So this is really, the area of a big sphere is really 4 times whatever the area of a particular circle is. So what we need to do is we need to take this 1362 watts per square meter and divide by 4, because that's how much energy is going to be spread over that entire the entire sphere of the Earth. So this is more or less an average value that we're going to get. This would be at max, or at peak potential, like at noontime. This would be average. So let's go ahead and divide that out, which makes it all the more depressing, actually. So we're going to divide by 4, so we get 340 watts per square meter. So this number is a little more realistic. So if you had a solar panel at the top of the atmosphere, and it was collecting the energy needed to power everything inside your house, you could operate 3 100-watt light bulbs, and that's it. No energy left over for your hot water heater. No energy left over for your television. No energy left over to charge your cell phone. No energy left over to open the garage door with the garage door opener. You quickly, and if you have a electric stove, nowhere near the energy needed to be able to cook. So you start to see that the possibility, the potential for solar energy starts to decrease drastically, because the best you can do in terms of an average value is 340 watts per square meter. That's basically 3.5 100-watt light bulbs. It's not a lot of energy. All right, now let's go down to the next one. And it gets a little more actually depressing. Roughly 58% of the sun's energy that falls on the Earth's atmosphere lands on the Earth's surface. Roughly 23% of the energy is reflected back into space by the atmosphere, and 19% is absorbed by the atmosphere. So how much energy lands on the Earth's surface at one time in watts per square centimeters, or watts per square meter? Because you might be thinking earlier, well, it's not feasible to put the solar cell at the top of the atmosphere. That doesn't make any sense. You have to have it on the ground. Well, if you put it on the ground, now all the energy that strikes the Earth's atmosphere is going to get to the Earth. According to this number, it's roughly 58%. Now, you can argue a little more, a little less, but it's a good number to work with. So what we need to do is we need to actually take this number, 340 watts per square meter, and multiply it by 58%. And that'll be a number that's a little more realistic, because not all that light hits the ground. So now it comes out to be 197. I'm just going to round it off to 200. Remember, this was roughly over here, so it's not an exact number, but it's a good ballpark number. So now we can't operate 1,300-watt light bulbs or 3.5 100-watt light bulbs. We can only operate 2. with nothing left over for cooking and for watching television or heating your house or heating your water. There's nothing there. So that becomes pretty depressing real quick. All right, let's move on to the next one, letter D. If typical photovoltaic cells, there's a typo there. If a typical photovoltaic cell converts only 20%, now some are better. The ones that obviously NASA uses are going to be a little more efficient because they have a lot more money to spend on these things, but a photovoltaic cell that you might put on your roof isn't going to have as great efficiency as one NASA might use. So it might be in the range of 20%. Now, it's not an exact number, but it's a good ballpark number for us to use. It's realistic. So if a typical photovoltaic cell only converts 20% of the sun's energy instantly upon its surface, how much energy per square meter is collected by a photovoltaic cell? So, yeah, 200 watts per square meter hit the earth, but that cell is not going to be able to convert all that energy into something you want. So we need to multiply this by 20%. So 20 watts per square meter times 0.2. So pull it in here. I know some of you can do this in your head. I'm just showing it here. It's going to be 40. So we're talking 40 watts per square meter. Now you can't even operate one light bulb. And you have nothing left over to live on. So you could operate one 40-watt light bulb. And 40-watt light bulb's not enough to, barely enough to read a book by. So we've got some serious issues here. Let's go to the next one. The dimensions of LHS's solar array are roughly 1 by 6.4 meters. If it collects 1 kilowatt of energy, determine the number of kilowatts per square meter and compare your answer to letter D. All right, so let's do a quick calculation. So if you're just watching this video and you know solar panels, well, our school has I think about 8 solar panels. They're located on top of the science room, and they collect the energy needed to operate the lights in the physics room. So it's kind of a little science experiment that we're conducting, and we got a grant for it, and so it's working out real well for us. So what we want to do is this. I know that it produces 1 kilowatt of energy. We've got ways of measuring that. And we know what its dimensions are. So what we're going to do is we're going to actually calculate how many kilowatts per square meter. So we'll go ahead and do that. So we know it collects 1 kilowatt divided by the area, which is going to be 1 meter times 6.4 meters. And we'll divide those out. So we got 1 divided by 1 divided by 6.4. And that gives us 0.156, and that's going to be kilowatts per square meter. Now you might be like, hey, that's nowhere close to what we have up here. Well, let's do a quick conversion. That's going to be 5. If we convert it from kilowatts to watts, it's going to be 156 watts per square meter. So that's what we're collecting. Now the problem is that's at maximum. That's like at noon in the summertime. That's the maximum value. Now, what's kind of interesting is that's somewhat similar to what we had up here. So that's about the best we can get per square centimeter, or per square meter. And that's the fact that we've got, fairly big array. So 156 watts per square centimeter. This is kind of interesting. All right, flip it over, and we got one more over here. So if an average American uses 9.36 times 10 to the 8th joules, which converts to 260 kilowatt hours of energy per day, how large of a solar panel will he or she need to meet his or her energy requirements? So the question is, if this is true, if this number down here is true, then on the average, we're going to collect 40 watts per square centimeter, or per square meter. I keep saying square centimeter. And you want to say, all right, enough of fossil fuels, enough with the nuclear energy. I only want to go solar. Well, and you don't want to change your lifestyle. how big of a solar array would you need if that's the best you can do? So we got 40 watts per square centimeter. So I'm going to go ahead and write that up over here. So 40 watts per square centimeter. And I know that I use basically 9.36 times 10 to the 8th joules of energy per day. Someone in their infinite wisdom calculated that. I don't know if it's totally correct, but it's a good ballpark figure for us. So I'm going to write that down. 9.36 times 10 to the 8th joules per day. All right, now, I need to convert this. This is in joules per day. I need to convert this from joules per day to joules per second, because joules per second is a watt, and I have something here I can use then. So, quick conversion. 1 day is going to be 24 hours. 1 hour is 3,600 seconds. And then let's plug that into the calculator. So 9.36 times 10 to the 8th divided by 24 divided by 3,600. And I get 10,833. So 10,800. Wrote that wrong. 10,833, and it'll be joules per second, which is the same as 10,833 watts. All right, now that's basically the amount of energy consumption I'm going to be needing. It's about 10,000 watts, 10 or 11,000 watts to function for an average. Let's see, how do I want to say that? This is the number of watts an average American needs to be able to function currently. Now I'm going to do a conversion. So 40 watts per square centimeter. Notice what happens to my watts. They cancel out, and I'm left with how big of an area I need. So I'm going to take that 10,833 and divide by 40, and I get 270 square centimeters. I'm sorry, square meters. Now, you might, well, how big is that? Is that the size of a roof? Well, let's just pretend that this is a perfect square. So this solar array is a perfect square. Well, the equation for a square is side squared, side times side. So if this is the area equals side squared, and I want to know what the side is, I just got to take the square root of the area. And if I do that, so I need the square root of that number, I get 16.4. Let's just say 16. 16 meters. All right, how big is 16 meters? I'm thinking here. I'm thinking. I have done something wrong here. Why did something not work out? No, that'll work. That's good. That's good. All right, so then we get 16 meters. Now 16 meters, how many feet is that? So let's just multiply basically by 3. It's not a perfect conversion, but it's close. You're talking 50 feet. So if you want, that's 50 feet on a side, which, roofs these days are about that big. So it's 50 feet on a side. So you'd have to cover your entire roof with solar panels to be able to make this work. Now, problem is that's for one person. What if you have 2 people that live in that house? You have to double the area, or not use as much energy. So you got a potential predicament. And the question is this: is solar energy all it's cracked up to be? You watch the news and you would think that the answer to all of the world's energy problems is solar power. And to some extent I would agree. But you can see by these numbers, you're going to have a solar panel the size of your house just to meet the energy consumption of a typical American. You put 2 people in that house, you're going to have to double the size of the roof. How realistic is that? Well, there are some factors that play into this. Obviously, we want to go ahead and continue to develop more efficient means of using energy, high efficiency dryers, high efficiency wash machines. So we want to continue to manufacture or improve the efficiency of the technology that we have. And that's a good thing. That'll reduce this number right here. That'll reduce our energy need. The other part of this is this 20% business right over here. Right now, solar panels are only about 20% efficient. That doesn't mean that there aren't solar panels out there that are more efficient, because there are. They're just more expensive. And I think as time goes by, if we can make this number go up, and the higher the number, the better off we're going to be, and we can make this number go down, the amount of energy we need, then, hey, then maybe solar energy might be able to meet our needs. But I don't think it's going to totally replace all the other sources of energy that are out there. I think there's still going to be a need for fossil fuels, still going to be a need for nuclear power, and some of the other ones. Wind, I don't think we're getting a lot out of wind, but I think those needs are still out there. But I think it's something. I think solar power is worth our investment in the future. But it might be a while before we actually see the benefits of it. All right, that's the video on solar power. When we come back on the next video, it's going to be conservation of mass energy.